So this is a demonstration on fractional distillation aimed at Key Stage 4 chemistry. It applies to both double and triple exams, and it shows you how we refine crude oil to make useful products. One of the problems is that we can't really demonstrate this in class anymore, because even in this slightly less dangerous version there are still carcinogenic chemicals that cause cancer, so we're not really permitted to light these in front of you, so we're doing it as a video demonstration for that specific reason. This is a setup for simple distillation that you may recognise from Key Stage 4, and it's a very good way of separating two liquids that have different boiling points. For example, if you had a mixture of alcohol and water and you wanted to separate them out, you could put the mixture into here. Alcohol has a boiling point of around about 78 degrees Celsius, and water, as you are well aware, has a boiling point of 100 degrees Celsius. If you heat this until it starts to evaporate and the vapours have a reading here that is above 78 but below 100, you will be evaporating the alcohol but leaving the water in there. The alcohol will go down this part, this is called a condenser, and it has cold water running around the outside. I'll show you. It doesn't have anything running around it at the moment, but if I switch the tap on, you will see cold water running from the bottom to the top. The tube is double glazed, so the centre of the tube doesn't contain any water at all, but the outside sections do. So watch carefully. So the outside of the tube is double glazed. If we run water from the bottom to the top, you can see that it will cool the tube. It's very important to run it from the bottom because you want the coldest part of the apparatus to be here, so that any vapours, if we were boiling alcohol at 78 and it passed through this tube, it's hitting water that's at room temperature, about 20 degrees, and it will condense back into a liquid, and we can collect it out of the end in a test tube. So we would be able to distill off the alcohol very easily. Now this method is used in making strong alcoholic drinks. So if you wanted, for example, to distill wine to make port, you could do that by boiling off some of the alcohol, and you'd end up with a stronger solution of alcohol at this end. Now that's fine when you've got two liquids, but the thing with crude oil like this, crude oil is a mixture of about 50 different compounds. Now those compounds are known as hydrocarbons. They contain hydrogen and carbon only. And the type of hydrocarbon contained in crude oil is known as an alkane. An alkane is a hydrocarbon that only contains single bonds. It is sometimes referred to as a saturated hydrocarbon for precisely that reason. So a lot of key words there: hydrocarbon, saturated, alkane. There are several alkanes, 50 in crude oil. They range from the smallest, which only has one carbon and 4 hydrogens, CH4, that is methane. This one is C8H18, which is octane, more commonly referred to as petrol. And they range right the way up to C50H102, which you would know as tar, the stuff they use to lay the roads. Now, all of those are useful compounds, but as a mixture, it isn't very useful, so we need to separate that mixture. So we can do that in the same way. So, for example, if I put my crude oil in here, you'll notice there's some little granules at the bottom. They're called anti-bumping granules. That is just to stop it boiling too vigorously, so don't worry about them. They're not part of the process as such, and you don't need to know about them for your exam. They're just really for my safety. I'll pour a little bit of the crude oil into the apparatus. Like so. And you can see that it's quite a sort of dark liquid. And it, on its own, you know, if you put that into a car, it would destroy the engine, because that's a mixture of all the different hydrocarbons. We've taken out some of the most dangerous ones, the longer ones like the tar, because of the cancer risk, but the rest of them are in there. So there's quite a big mix of hydrocarbons. So that would contain some methane, it would contain some petrol. It would also contain longer hydrocarbons like diesel, which is about C20H42. All of them have different boiling points. The boiling points of these alkanes, of these hydrocarbons, are based on the molecular size. And the pattern is really quite straightforward. What is holding the hydrocarbons together is just weak intermolecular forces. Yeah? Don't get confused with the idea of these things here. These are covalent bonds. These are very strong. In order to break one of these, you need a much higher temperature, and that will be covered in a later topic called catalytic cracking. So these do not break. When I'm heating this using a Bunsen burner, it simply won't have enough energy to break covalent bonds, but it will be able to overcome the intermolecular forces. Now, the intermolecular forces between petrol are going to be a little bit stronger than the intermolecular forces between, say, something like methane. The reason why is that petrol has more points of contact, so the molecules are more likely to be tangled together. That makes the forces stronger. So therefore petrol has a higher boiling point than methane. The boiling point of methane is well below zero, so methane is a gas at room temperature. The boiling point of petrol is about 70 degrees Celsius. So it's a liquid at room temperature, as you should know. And that means at 70 degrees there'll be enough energy to make these separate out and turn them into a gas. So we're going to try and do that now. I'm going to heat this mixture. So we're going to try and heat this to about 70 degrees using the thermometer here, and we'll try and see if we can collect some petrol. Now, it's very difficult to control the temperature using this crude equipment and Bunsen burner, so it's very unlikely I'm going to get pure petrol. I'll probably get a mixture of hydrocarbons that contain some petrol if I'm lucky. Now you can see the vapours are starting to come down the tube, so I'm going to see if I can collect them at the end here. You can see it starting to drip down again as it condenses again. That's quite difficult to get. To get the actual fuel. Temperature's about 100, so it won't be pure petrol. It will contain some slightly longer hydrocarbons as well. So this will probably contain a little bit of naphtha, which is about C10 to C12. The darker materials are staying in the tube, and we've got some fuel dripping through now. So I'm going to leave that. I've managed to collect a small amount of short-chained hydrocarbons, so roughly this length, maybe a little bit longer, and that means they should catch fire quite easily. So I'm going to pour some of it into a watch glass, and if we try and light it, you can see that it burns with a quite blue, slightly yellow flame, and it burns quite cleanly with little smoke. I'm going to heat the apparatus to a higher temperature. It is now getting to about 140 degrees. Now if we go up to above 160, so we should be collecting diesel at this point. Again, we've got a clear liquid, but this time it's not quite as runny, it's a little bit thicker and more oily. So if we try and light this one, I'll switch the lights out again. So you can see it's a yellower flame. You may be able to see that it's more smoky, causing more pollution. And that is because it's a longer chain hydrocarbon. They do not burn as well, they tend to do more incomplete combustion, which is something we'll talk about in a later demonstration. You have two major problems if you're thinking about oil refining. One, it took me about 10 minutes to obtain two very, very small samples of hydrocarbon. So the equipment is just too small, we need to do it on a much larger scale. And the other problem is I had to heat it to two separate temperatures on separate occasions in order to get my two separate fractions, my two separate components, which are petrol and diesel. If I were to add another condenser on top of it, which is further away from the heat source, I could control it so that the temperature of this one was at the 180 degrees for diesel and this one was at the 70 degrees for petrol, and I could get the two of them separately. Now that's quite difficult to do, and I'm not going to demonstrate that now, but effectively that's what fractional distillation does, is they have a stack of these condensers all on top of each other on a very large scale. What happens in a proper oil refinery, this fractionating column here will be very large. Yeah? If you imagined a person standing next to it, it'd be about that big. So this is very large, it will refine an awful lot of crude oil in one go. The crude oil is heated here. Now this is enough energy to break those intermolecular forces between all the hydrocarbons, or pretty much all of them. Anything that doesn't boil at that temperature, where those intermolecular forces are too strong, will come out the bottom as the thicker parts of the crude oil. So things like lubricating oil and asphalt, which is effectively the tar that goes on the road. Everything else will evaporate and turn into a gas because these intermolecular forces are overcome. Remember that you have not in this apparatus broken any of these. These are strong covalent bonds. They require an awful lot more energy to break them, and they will not break at temperatures below 500 degrees. The gases rise up, and as you go up the column it gets colder because it's further away from the heat source. As the larger hydrocarbons rise up the column, they will turn back into liquids and they get tapped out, a little bit like I showed you on the simple apparatus beforehand. And that separates the different products of crude oil very effectively for different uses. So the gases that come out the top are things like methane, that's used in gas cookers and that's used in the Bunsen burners in your school laboratory. Then you've got gasoline or petrol, which is octane, that's about 8 carbons in length. You then get to kerosene, which is used in aircraft, that's about 15 carbons long. Diesel, which is used in many cars nowadays and also lorries and ships, which is about 20 carbons long. Fuel oil, right, which is used in things like power stations, and that is even longer, that would be about up to 30 carbons long, and then the ones that are over 40 carbons long come out the bottom.